All right, so the big thing on this one is when we're writing equations, we're actually going to go backwards on this one so that in the past we had been giving you the question. You had to tell me what the answers was. This one, I'm going to give you the answers. You got to tell me what the question is. So you're basically working this thing backwards. Okay, so basically it's going to be set up this way. It's going to be find the equation with solutions. X equals -2, or X equals 2, and X equals -5. Okay, so everything is backwards. And it's almost one of those, if we could start at the bottom and work our way back to the top, basically is what we're looking for. Now for this one, notice we've got two solutions, correct? So guess what our highest power is going to be? It should be x squared, right? So when we get finished with this thing, we know we're looking for an equation that's got x squared in it. If we had three solutions, we know we're looking for x to the third. So based on the number of solutions, that's how many answers it is that we're looking for. Okay, so the very first thing is that I guess the last thing we had before this one is that right before we had these solutions, these things were set equal to 0. So we're just going to move whatever number we have. So we've got this thing set equal to 0. So in this case, we would subtract 2 for this one to get it back to x minus 2 equals 0. This one we would add 5, and then get x plus 5 equal to 0. Okay, and we had these two things separated, and before that, these two things were actually together. So then we had an x minus 2 and an x plus 5. And then once we had these two things together, then we get to do the full method. So then we've got x times x for x squared, x times 5 for 5x, -2 times x for -2x, and then -2 times 5 for -10. Okay, and then put these two things together. So we've got x squared plus 3x minus 10, and that would be an equation that we're looking for. Yeah, so we've got x times x for x squared, x times 5 for the 5x, -2 times the x, -2x. There you go. Yeah, so it's double distributive property. Okay, now here's the thing for this one. All we're going to need now, that is the answer we're looking for, but realize that there possibly could have been a greatest common factor that was taken out of this thing in the beginning. So, and that's something that will, for those of you going into pre-cal, that's something you actually check for later on in pre-cal, because it could have been that this thing was whole multiplied by 2. So it could have been that you would have, and again, you don't have to write this down, it's just talking. It could be that everything was multiplied by 2, that this thing could have been 2x squared plus 6x minus 20. Or it could have been everything was multiplied by 4. It could have been 4x squared plus 12x minus 40. Something like that. So but all we're going to worry about is just getting these in here. We don't know about a greatest common factor. So for that part of it, we're not going to worry about it. And again, if you're going into pre-cal, we'll actually show you how to find out if there was a greatest common factor based on some things for what we're going for that part. Okay.
Go back up so I can see the title.
Okay. Now, one thing before we get to the next example, we actually have to kind of go back and talk about something I think we talked about a while back, but it may have kind of slipped past. So let's let me go back and talk about a few things here for this one. All right, so we talk about complex solutions and radical solutions. Okay, so if we're talking about complex solutions and radical solutions, the way these things are set up, because if you remember yesterday when we were working through and doing one of the last answers we had, how we got the complex solutions that we had, and we square rooted we had a negative number, we had to square root it, so we had the plus or minus I for that one. Same thing if this had been like, x squared equals 10, and we had radical solutions, we'd had, x squared equals 10, we would have square rooted it, we had the plus or minus square root of 10. So that whenever we're doing these, whether it's complex or radicals, those two answers are always going to occur in conjugate pairs. Because now, again, yesterday we found a shortcut on this one, but most of the time for those, it's going to be coming out of the quadratic formula. And because of the plus minus that's in the quadratic formula, if this is a complex answer, you're always going to have two because you're going to have the plus or the minus that goes with that one. If this square root doesn't simplify, same thing, you're going to have two answers because you're going to have the plus or minus there. Okay, so what that means, and I think we may have talked about that once upon a time with the conjugate pairs. If we didn't, then at least we've got it here. So let's do this one. I'm going to give you a solution, and then we're going to find the conjugate solution. Okay, so let's say we're going through, we have to use the quadratic formula. We actually, get this thing out, and we get, 2 minus 3i. So if I ask for a conjugate solution, it's going to be 2 and then plus 3i. So whatever, if it's a radical or if it's an imaginary number, whatever sign's in front of that imaginary number, you just need to change that from positive to negative. Or if it's negative, change it from negative to positive. So if the answer was square root of 7, they say find the conjugate solution that would go with that one. It's going to be negative square root of 7. Same thing if it's 4i for a solution. Conjugate solution is just a negative 4i. And then the one that sometimes throws people off a little bit. If you have negative 3 minus the square root of 2. Because sometimes that first number being negative throws them off a little bit. So like, all right, so what do we change? Both signs here? For that one, no, you still only change whatever's in front of the radical or whatever's in front of the imaginary number. So this one would be negative 3 and then plus the square root of 2. Okay, so that's one thing that for the next problem we look at, you got to kind of have that in the back of your mind, that if they give you a solution, there's actually, it's imaginary or square root, radical with it, there's actually two solutions that's going to go with that one. Let me see. Actually, let me start this on the. Everybody good there? I'm going to go to the next page. I'm right towards the bottom of the page here. Line. So we're going to write the equation, given the solutions. Negative 4 and 2i. Okay, and sometimes with this one, the way they word some of these, they might not give you even the x equals we had on this one. So probably the very first thing you'd want to do for this one is, if that's what we have here, that's our two solutions. That means we've got x equals negative 4 and then x equals 2i. Okay, so that's what we were given. The one thing extra that you've got to kind of get from this one is if they give you this answer that's 2i, you also have to just know that if 2i is an answer, then we also have negative 2i. All right, so we've got x equals negative 4, x equals 2i, x equals negative 2i. We've got three actual, even though we were only given two, we know there's going to be three solutions because of the imaginary one. So for this one, we know the answer should end up with x to the third because we've got three solutions. Okay, so then rearranging on this one, we'll add the 4 back over here, make that x plus 4 equal to 0. Bring this back over by subtracting it. Bring this over by adding it. Okay, and then bring all 3 of those together. So we've got that. Okay, which means we've got to go back and do distributive property, do the full method again on this one. But here's the catch for this one. When you get it where we've got imaginary numbers, or even if you've got radical numbers, if this was, square root of 2 instead of 2i in this case, you still want to multiply. So you want to use your full method on the radical or complex numbers first. So before we do the x plus 4 times x minus 2i, we're going to do the full method on this part of it first. Because when we do that with the imaginary numbers or the radical numbers, it's actually going to kind of clean itself up a little bit. So we're actually going to get rid of some stuff in there that's going to make this thing, in the beginning, it's going to look kind of bad. But then when we clean it up, it's going to go, oh, that's not really as bad as it looked like it was going to be. Okay, so if we go through and do the full method on this part of it first, we're going to do x times x for x squared. We've got x times 2i, which would be just 2ix. And the order you put those in doesn't really matter. As long as you've got a 2 and an I and an x in there somewhere, order doesn't really matter. When we go underneath here, negative 2i times x, that's a negative 2ix. We get a negative 2 times a 2, that's a negative 4. And remember, if you do I times I, that is I squared. Okay, now here's why you want to do that imaginary part first. Because what happens in the middle when you do 2 minus 2? Cancels out, which is great because now that part's just gone. With the I squared at the end, that's just negative 1. So we've got negative 4 times negative 1, which means this is just going to be x squared plus 4, which looks a whole lot better than what this thing was going to start off looking like for that part. Okay, so if we take everything that's here with the imaginary numbers and do that part of it first, we're left with this. And now we can just bring down this x plus 4 that was in the beginning, and we'll get to do the full method one more time. Okay, so we've got x times x squared for x to the third. We've got x times 4 for 4x. We've got 4 times x squared for 4x squared. And we've got 4 times 4 for 16. Okay, and then I guess the good news on that one is all the terms are different, so you don't have to combine any like terms. The only thing you might have to do, Math Excel will probably take that. That's one of those that if we're doing this online, I tell you to write it in standard form. The numbers are correct. You just want to put them in the correct order, so bring them down in descending order. So it'd be x to the third plus 4x squared plus 4x and then plus 16. So this is good. That's even better if we're looking at how it should be written. Ooh, now, here's kind of the next thing we'd be going with this one. I don't think they would ask you to graph this one because how are you going to graph imaginary answers? How are you going to plot that? Because we know x equals negative 4. It's going to cross at negative 4 on the x-axis. How are you going to get this to cross at positive and negative 2i? Probably not, right? Because it's imaginary. It doesn't really exist in that case. So this is probably one of those problems where you wouldn't be asked to graph. But let's just kind of back it for a minute if we could graph this one. What's the end behavior on this graph? And how do we know it? Okay, now I guess 2 things we can do from this. We know what the y-intercept would be. Everybody okay with that one? What would the y-intercept for this graph be? Be 16, right? So even if it's like this, where it's x to the third, whatever the c value is that's here, that's still your y-intercept. So we know it would cross the y-axis at 0, 16. So the last number, as long as it's written out where it's not in factored, if it's in factored form like this, you have to write it all out, multiply it all together to get it to here. That would be our y-intercept. In behavior is based on the first number, correct? So this is a positive x to an odd power. Does anybody remember what your left and right in behavior is going to be if you do that one? It's going to be up and down. So if it's positive, it's like a positive slope. So the right side should be up and the left side should be down. Because again, that would go back to the first term here based on x to the third. That's a positive number x to the odd. So if it's an odd power, it's like slope in the direction that it goes. Positive slope, the right side's up. The left side's going to be down. Okay, so that's kind of leading us up to where we're going to go with the next part, which is kind of going back to the graphs on that one. So that one, again, probably with the I terms like this, you're probably not going to be asked to graph that one because that's going to be kind of hard to graph. That we know we've got it crossing at -4. This part means it's really not going to be crossing the x-axis, so probably just going to have that one number that's there, and then the graph would cross the y-axis at 16. After that, we'd have to just plot some points and just kind of figure out where this thing is going to go. Okay, so if we're tying this back into graphs, though, we're looking at zeros of polynomials. Okay, and for this part of it, with the zeros of the polynomials, this is all based on the multiplicity of the zeros with the equation in factored form, which again means you're going to have to go back through and factor this equation, this particular one that we're working with. And when we're talking about the zeros, again, that's the roots, that's the solutions, that's the x-intercept, whatever you want to call it. The multiplicity is basically this. That's your powers. So when they talk about multiplicity, that's just another way of saying what is the power of this equation that's in factored form. Okay, and here's basically what it comes down to. If you have an odd multiplicity, and that is not multiplicity, just in case anybody's wondering, it's multiplicity. Again, multiplicity just means it's the power. And based on the multiplicity, it's going to have the graph do certain things for this one. If it's an odd multiplicity, the graph at that solution, which again, when they're talking about solutions, basically we're talking about at that particular x-intercept. If it's an odd multiplicity, it's going to cross through the graph. Okay, which basically means, if I kind of give you a visual on this thing, if we were doing this one, if we go back to this last problem we had back here, we had x equals -4. So if that graph was at x equals -4, we know that was going to be an x-intercept we had. That if this thing was odd multiplicity, which it was, because there was only, if we go back to this one, it had x plus 4, it basically was to the first power, so there's only one x plus 4 that was there. Then that means this graph has got to cross through, so it does something like that. Okay, if it's an even multiplicity, or again, even power, the graph turns around at that x-intercept. Okay, so odd multiplicity, it crosses through the graph. Even multiplicity, it's going to turn around, which means if we were doing this one, we were back here at -4, like if we were doing another problem. If we had graphed that one and had x minus 4, if we were graphing it, and this was x plus 4 squared, instead of just x plus 4, so if that solution had been there twice, then that graph is going to do something like that. Because basically that's like x squared, right? And if remember, had x squared, had we had a peak in the graph, or it could have been that it was maybe going this way. But basically, if it's an odd multiplicity, that graph crosses through the graph. If it's even multiplicity, it's going to turn around at that point. Okay, so what we're going to do is we're going to give you a couple problems on this one where we're looking at the graphs on these and kind of seeing what's happening with it, and show you what you're going to do and how. And this is where we tie everything together on the graphs. This is where we kind of put all this together in one nice big package here. So we're going to solve this equation. X plus 3 times x minus 4 squared equals 0. We're going to state the multiplicity. Of each root, each solution, each x-intercept, ever how they want to call it. Again, you can basically interchange about 6 different names with that one. It's the root, it's the solution, it's the x-intercept, it's the answer, whatever how you want to say it, all those different things there. We're also going to determine the end behavior. And then the last thing we're going to do is we're going to sketch the graph. Okay, so we're going to look at this with 2 different ways. This first problem we're going to do, we're going to have it so it's already in factored form, so we don't have to go through and factor it. The next one we're going to do, we're actually going to solve it, break it down, and factor it, and then show you how that one looks. Okay, so if it's already in factored form, finding the solutions, finding the roots, finding the answers, whatever it is they're going to tell you to solve, should be really easy. You're just going to take this x plus 3 and set it equal to 0. Then we'll do the same thing with the x minus 4, set it equal to 0. Okay, so this one will subtract 3, so we get x equals -3. This one will add 4, so we get x equals 4. Okay, so if it's in factored form, finding the solutions is really easy. Just take each one, set it equal to 0, add or subtract away the numbers. If there happened to have been a 2x here or a 3x over here, after you do that, you would go back and divide by whatever number is with the x. And you got it. Okay, multiplicity should be pretty straightforward as well. We're just going to put MULT for short, just to make it go a little bit quicker. Okay, so for this one, x plus 3, you're looking for the power that's with x plus 3. It doesn't have a power, so it's understood to be 1. The x minus 4 was x minus 4 squared, so that would have a multiplicity of 2. So x equals -3 has a multiplicity, again, which is the power of 1. X equals 4 has a power multiplicity of 2. And again, what those things do tells you what the graph is going to do at that point. So because 1 is an odd number, that means that at this point we're going to cross through. Okay, and because this 2 is even, that means when we get to this point, we're going to turn around. So before we get to the end behavior, we're gonna get back to that in just a second. Everybody okay with that first part there? Everybody okay with the solutions and where we got the multiplicity and what happens through it? Okay, so graphing this one. We've got -3 and 4. So we know we've got a solution at -3, and we got a solution at +4. Okay, now the question is, now again, we know that at -3 it's going to cross through, and at +4 it's going to turn around. The question is, does it turn around like this, or does it turn around like this?
It's positive, so it might
Okay.
go up.
Well, now here's where we got to kind of tie in. Here's where we tie everything in. Here's where the end behavior is huge on this one. So at this point, it's in factored form. To get what this end behavior is going to be, we've got to basically go back and multiply this stuff together. All right, but we're going to do a little bit of a shortcut because what's in the middle, figuring out what's in the middle is the factoring part. We just need to worry about what the first term was, just like back here. That to get the end behavior, all we need is the first term. So all we need to worry about on this one is what happens if we multiply x times x squared. We get x cubed, right? So we got x to the first power, we've got x to the second power. If you put that together, we've got x to the third power. So for this one, it's going to be x to the third power, and they're all positive up here, correct? So it's going to be a positive x to the third for the first term. So that means, again, it's kind of like the last one. That means the left side is going to be down, and the right side is going to be up. Okay, now here's where that ties in. Here's what that means for this one. That from the rightmost zero, from here, this thing has to go up. Like that. And from the leftmost zero, after we go to that zero, from there, we have to go down. So it's got to go through like that. So if it's crossing through at -3, it's going this way. It's still going to keep going this way. And because at 4, it turns around when it gets to here. That means it's got to turn around, and eventually it's going to come back and meet somewhere back up here where those two things are going to be. Okay, now exactly where that point is, that's not a huge deal. The main thing really in this one to be concerned about is, how this graph turns here and what it does here. So at each one of these zeros, that's going to be the huge thing we're looking for is which way it turns around and how it goes. Because that's one, I can make that a multiple choice question where that every one of these has 4 different, even using these same 2 solutions, we can have it do different things and just go all over the place and do all kinds of stuff. So that's where this crossing through and turning around is huge when it comes down to it. Question.
So in the homework.
So again, turning points, this thing is coming down and then it's going back up. So that's one turning point. This one, it's going up and then it starts to come back down over here. So that one, we'll have 2 turning points. And really the only way to know the turning points is just to do a sketch of the graph. And once you do the sketch, you can kind of see how many times this thing would turn. Okay. And the other thing with that one too, this would be, because this is a low point at this area, this would be a relative minimum because it's one low point here. When you get up here, this would be a maximum point. It'd be a relative maximum. It's not the highest point because, again, this is going to go forever over here. But just right in here, that's one mountaintop in this area. So that would be a relative maximum up here. That would be a relative minimum back over here. Okay, so let me show you. That's one where it's in factored form. Let me show you one more where it's not in factored form. We'll work through it, do the exact same thing, and then that'll wrap us up for today. Now, if somebody's wondering, how would we find out, exactly where this thing would peak out? This would be one of those things where you could take, just like with this one back here, we knew that the y-intercept for this one was at 16. If you went back and multiplied all these numbers together and find out what that constant would be, that would tell you this thing would cross. Basically, you've got -4 squared, which would be 16. And then we would do 16 times 3. So this thing would have a y-intercept at 48. Because you're going to do -4 times -4. When you do the full method, then you would do that times the 3. So that would tell you this thing is going to cross the graph somewhere up here at 48. All right, so the last one here. Okay, so let's go x to the fifth plus 4x to the third equals 5x to the fourth and then minus 2x to the third.
Oh.
Okay, so first thing with this one is it doesn't equal 0. And if we're going to factor, we're going to solve most things, it's got to equal 0. So we're going to move these things back over. So if we add the 2x to the third over here, we can put that one there. And if you want to do two things at one time, go ahead and move the 5x to the fourth over. We'll subtract 5x to the fourth. And that one would go in between the x to the fifth and the x to the third. So basically, we could put that one right in there. So that would cancel out. We got that would cancel out. We got x to the fifth minus 5x to the fourth plus 6x to the third would equal 0. Okay. And again, you don't have to do all that one. We did two things at the same time. If you want to do them separately, do one time, one part of it, and then move the other term, that's fine. Okay, here's where the factoring sheet comes in handy. We've got three terms, correct? If it's three terms, is there a greatest common factor? Do they all have something in common? They all got x's, right? Yeah, so take out the smallest amount of x's, which would be x cubed. That'll leave you with x squared minus 5x plus 6 equal to 0. All right, if we cover up x cubed for just a minute, does that look like something we could factor? Yeah, so now here's where we got to be careful because it could be 1 and 6. You could do 6 minus 1 or 1 minus 6 and get negative 5. You also could do negative 2 minus 3 and get negative 5. So a lot of times people go at this and I go, oh, I know it's got to be 1 and 6 because I'll do 1 minus 6. Well, it also could be negative 2, negative 3. So this is where you got to be careful of your signs. So it's the factors of positive 6 where the sum is going to equal negative 5. Okay, B term is negative. Bigger number has to be negative. If you divide a positive 6 by a negative 6, that makes that a negative 1. So that means the 1 and 6 is not going to work. It's got to be 2 and 3. Okay, so factoring what's on the inside left over, we get down to x minus 2, x minus 3. This x cubed is still on the outside. Okay, so there it is in factored form. So when we set these things equal to 0, it's still x cubed equals 0, which means that would just be x equals 0. We set the x minus 2 equal to 0, that's x equals 2. We set the x minus 3 equals 0, that's x equals 3. Okay, and somebody may be saying, all right, it's x to the fifth, we're looking for 5 solutions, correct? Well, x to the third, just because it's x to the third, just means this answer repeats 3 times. So we talk about the multiplicity. X to the third would have a multiplicity of 3. X equals 2 would have a multiplicity of 1. And then x equals 3 would also have a multiplicity of 1. Okay, and I guess you could call this good news. They're all odd, which means that every single one of these numbers is going to cross through. So none of them turn around. All of them keep going through as we go through the parts here. Okay, so we've got our solutions. We've got our multiplicity. And the good news with this one is that because this thing was already written out like it was, we know that x to the fifth was our highest power. So again, if we go in behavior on this one, it's a positive x to an odd power. Oh, can't see that. There we go. So this one's going to have this graph similar to what we had on this one. Okay.
How did you get the multiplicity again?
Oh, so your multiplicity is basically the powers you had back here. So this one was x to the third. So it's degree 3, multiplicity of 3. The x minus 2, there's not a power, so it's an understood 1 that would be there. Same thing with the x minus 3, that's just an understood 1 that would be there. So whatever solution you're working with, you go back and look at it in factored form. This one was x to the third, so this one's going to be degree 3. Okay, so this one, like on the last one, left side is down, right side is up. Okay, so if we put it all together. What are our solutions here? We've got 0, 2, and 3. We've got 1 at 0, 1 at 2, and 1 at 3. Okay. Again, the end behavior, you really don't, we know they're crossing through, but again, we don't know if it's crossing this way or this way, where it's going to be pointed up or down. That's all based on your end behavior, because that's going to kick everything off. We know from the leftmost 0, it has to go down. From the rightmost 0, it has to point up. So we know that that part of the graph has to look like that, and we use those endpoints, that end behavior, to then figure out what's happening in the middle. So I know this crosses through, this crosses through. So this thing eventually has got to turn and come back and get to this one. Again, it's going to cross through, and then eventually they're going to turn and meet somewhere up here. Okay, now, what exactly the graph does, that's one of those things where if in pre-cal they've got more time to do that, that's where you would go back and then figure out how far down this thing would actually dip, because it could be that it goes way down like this, and then it may turn and come way up like this. For test-wise, all I'm worried about is that you know that it goes underneath here and above it here, based on the endpoints and the end behavior. Exactly how big or how tall, that part, it could be like this, it could be something in here. That part I'm not worried about. That's something, if we had more time, we'd dig into a lot more to see what that value would be. The main thing is just knowing the basic general shape of how this thing is going to go.